Okay, paper 3, question 1. So guys, remember this first kind of bolded part of the question is very important because it kind of tells you what's going on in the question. So it says a suitable site for the landing of a spacecraft on the planet Mars is identified at a point A. The shortest time from sunrise to sunset at point A must be found. So we're trying to find the shortest time from sunrise to sunset. So I'm guessing they want to land the spacecraft at night. They don't want the sun to be there because I guess it's too I don't know, it's too hot or too bright or something. So it says radians must be used, all values should be exact. Then it says Mars completes, right? So it's giving us some important information. Mars completes a full orbit in 669 days, which is 1 Martian year. On day T, where T is an element of Z, the length of time in hours from the start of the Martian day until sunrise at point A can be modeled by this function R of T, right? That's confusing, guys, because day T is an element of Z, which is the integers, the length of time in hours. So remember, guys, this is the graph here. So T is the number of days. So T is in days, and R of T is in hours. So think of R as the number of hours. So the number of hours changes. It's a bit like, it's like the seasons. If you think of it as the seasons, like on Earth in summer, there's more. So this is actually the shortest time from sunrise to sunset. So the shortest time is actually increasing. So yeah, this would be summer here. And then as it goes into winter, there's less time from sunrise to sunset. Okay, there we go. So part A, it says, show that B is approximately 0.00939. Okay, now B, hopefully guys, you remember from your transformations and your modeling sinusoidal graphs, that B is given by this equation. 2 pi over B is equal to the period. Now the period of this graph is 669 because that is 1 year, and then it'll just recycle. So 2 pi over B is equal to 669. Hence B is equal to 2 pi over 669. Now I'm guessing this is going to be 0.00939. Let's say approximately equal to 2 times pi. 2 times pi divided by 669 gives me, change that to decimals, convert to decimal, 0.00939 to 3 significant figures, 0.00939. Okay, part A is done. Part B. Mars completes a full rotation on its axis in 24 hours and 40 minutes. So this is what's happening. Mars, it's a bit like planet Earth. If you studied orbits or read anything about space or our solar system, the planets go around the sun, and while they're going around the sun, they also spin on an axis. It's the spinning that gives us the days, and it's the going around the sun that gives us the year. So one spin is a day. So Mars completes a full rotation on its axis in 24 hours and 40 minutes. So 24 hours and 40 minutes. That, by the way, is 24 hours and 24 and 2/3 hours, if you like. So 24 and 2/3 hours, which I would actually prefer to write it as 3 times 24 is 72 plus 2 is 74. So that's actually 74 over 3 hours. Okay, find the angle through which Mars rotates on its axis each hour. So think of it as it'll do one full rotation in 24 hours and 40 minutes. So what rotation will it do in 1 hour? So it's in 1 day it'll rotate a full turn, which is 2 pi. So 2 pi in 74 over 3 hours. So how much in in 1 hour, well, I just need to divide this by 74 over 3, or 24 and 2/3, or however you want to write it. I'm actually going to do 74 over 3 like this. Just be careful. I don't like decimals, guys, but you could use a decimal. It would be fine. So it's 2 times pi divided by 74 over 3. So this is my 74 over 3. Gives me 3 pi over 37. So the angle would be 3 pi over 37. That's fine. You could leave it like that. If you want to turn it into a decimal, it is 0.255 to 3 significant figures. 0.255. I should do approximately. Okay, that's parts A and B.